All right, number 8, and this is part C. So, block 3 of mass M3 is added to the system as shown below. There's no friction between block 3 and the table. So, we're asked to figure out what happens to the magnitude of the acceleration of block 2. If you look at your system, you already know that, wow, because this one's heavier, we're going to see acceleration in the downward direction from mass 1. And then mass 1 will accelerate up and block 2 will accelerate down. But then we've got to figure out, is it larger, smaller, or the same as the original 2-block system, and explain how you arrived at your answer. So the linguistic answer first here is that the acceleration will be smaller. If you think about what's happening here, the net forces that are accelerating this system are still going to be the same. The free body diagram that block 2 has still includes a force of gravity down. And remember, imagine that you can't see that upward force. It could be a Jedi, it could be anybody. It still is the force of tension upwards. Now we know that force of tension has changed because we have another block in the system that's changing things, but we still have the same applied force that's going to cause the system to accelerate. This force is now being applied to a system with greater mass. So we have the same applied force from gravity, on mass 2, and now we have a larger mass. So, without doing any math, you can think about Newton's second law, and that it says that the acceleration of a system is equal to the net force divided by the mass. So, if we have a force on the top that is staying the same, right? Then what we have here is a much larger proportional mass. This is a smaller number. So that's the sort of proportional way to reason through this problem. I'll also work through the mathematics right now so that you can see how that goes, okay? So this time I'm going to have 3 equations for what the net force is on each object, on object 1, on object 2, and on object 3. Imagine I put the stars on them in the order that I was speaking. So the net force on object 1 is going to be equal to, well, what does free body diagram look like? It's going to be the force of gravity on object 1 downward and the force of tension applied upwards, right? If I think about the free body diagram from object 3 right here, right? I'm going to have this force of tension this way and force of tension this way. So here's our first question we run into. Are those the same forces of tension? Not really. So I'm going to put a little 1 here to say that's the force of tension from object 1. And I'm going to call this one the force of tension from object 2. Which brings us to object block 2 here. We've got our force of gravity for block 2. And we've got a force of tension between block 2 and block 3 right there. Okay. So, just like we've had to do on some of our other problems, we have to think about which way is our positive direction and our negative direction now. We know the system is going to accelerate this way, so we'll call this positive. That means that this is the positive direction here, and this is the negative direction. This is the positive, and this is the negative. So that's going to help us as we think about a couple of our calculations in a second here. So back to writing out the algebra for my net forces. So the net force on object 1, and I'm going to use those positives and negatives right now. I've got the force of tension 1, that's a positive, with a minus, and I'm going to go ahead and skip ahead to mass 1 times gravity, right? Because that's what this force equals. It's the mass 1 times gravity. This one's going to be mass 2 times gravity. And we'll look up here that we are neglecting our two vertical forces here because they're equal and opposite because we have a normal force in the table. Okay? So that's going to be equal to mass 1 and the acceleration of the system. All right, this net force on object 2, our accelerating object. All right, we've got mass 2 times gravity. That's that force of gravity downward in the positive direction. And we've got the force of tension 2 that's in the negative direction. That'll be equal to mass 2 and the same acceleration that the other one has. Net force for our mysterious third block here is going to be force of tension 2 is in the positive direction, force of tension 1 in the negative direction. All three of these objects have the same acceleration, right? This A is the same for all of them. Okay, I've got a system of equations here, and I'm going to use the elimination method. I'm going to add them all together, and we're going to see the beautiful things that will disappear afterwards. So, I'm going to start with my left sides right here. So, I'm taking these three things right here, and I'm going to add them together. I'm going to do some rearranging as we go, just to make this a little bit easier. So if you're not sure what I'm doing, write it out yourself and rearrange your terms yourself. So when I add my left side of my equations together, I have force of tension 1 minus force of tension 1 plus force of tension 2 minus force of tension 2 plus mass 2 times gravity, the acceleration of gravity, minus mass 1 times the acceleration of gravity. If you're not sure what I did there, pause, check, do your own algebra. It's good for you. Now I'm going to add together the right side of my equal signs over here. So I end up with mass 1 times acceleration plus mass 2 times acceleration plus mass 3 times acceleration. Again, if you're not sure what I did, pause and check the video. I'm actually going to come up here and erase. Okay, everybody, weird pause, video magic. I took a phone call in the middle of that, so I have no idea what I was actually saying. So I'm going to erase this part right here so that I have a little more room to work out the rest of this algebra right here. So bear with me, more movie magic. Okay, so now you can see that our elimination method here does wonderful things for us. Force of tension from block 1 disappears. Force of tension from block 2 disappears. I'm going to rewrite this where I factor out G and where I factor out A, just so we can look at what our end result is. So we've got over here that G times the difference between mass 2 minus mass 1 is equal to A times the sum of all masses, where G is the acceleration of gravity and A is the acceleration of our system. So when I solve this for A, because remember that's what we're trying to do, we're looking for what happened to the magnitude of the acceleration, we have that the acceleration of our system is now the acceleration of gravity times the difference between our two hanging masses divided by the sum of all three masses. So when we think about what we had from part, I guess it's part B of the problem, so you look at your equation from above, you had that acceleration was G is equal to the difference between the two masses divided by the sum of the two masses. So right here we have that our new acceleration with the mass added, we have a larger number in the denominator now that we've added the third mass than we did when there was no mass sitting on the table. Because this is a larger number in the denominator, you can work through. If all the other numbers are the same here, we've got the same number, same number here, divided by something bigger than we did over here, which means that this acceleration for our new system will be smaller.